Welcome, everyone. Today we're diving into Chapter 5, Molecules and Compounds. In this chapter, we'll explore how atoms come together to form the substances that make up everything around and inside us. From the salt on your fries to the oxygen in your lungs, we'll look at how chemistry gives them structure and identity. Let's start with a sweet example, sugar. Table sugar or sucrose is made of carbon, hydrogen, and oxygen atoms. But if you've ever seen pure carbon as graphite or smelled hydrogen gas, you know they're nothing like sugar. That's the magic of chemical bonding. When these elements combine in just the right ratio and structure, they create something entirely new with new properties. Here's another example, table salt. Elemental sodium is a shiny, highly reactive metal. It can explode in water. Chlorine, on the other hand, is a poisonous yellow-green gas. Neither sounds edible, right? But when you combine sodium and chlorine, they form sodium chloride, common table salt. It's stable, safe, and tasty. The key takeaway is this: compounds have very different properties from the individual elements that make them. Most substances we encounter are compounds, not elements. You don't find free-floating hydrogen atoms in the air. Instead, atoms combine in fixed ratios to form compounds. That's very different from mixtures where substances are blended in any proportion. In compounds, there's order and precision. Look at this comparison. A balloon of hydrogen and oxygen gas is just a mixture. You can vary the amount of each gas. But a balloon filled with water vapor? Every molecule inside has exactly 2 hydrogen atoms for every 1 oxygen atom. That fixed ratio is what defines a compound. Joseph Proust formally described this idea as the law of constant composition. He found that no matter the source or size of a compound sample, the proportions of its elements are always the same. That's a foundational concept in chemistry. For example, break down 18 grams of water and you always get 16 grams of oxygen and 2 grams of hydrogen. That gives a mass ratio of 8:1. Whether you get your water from a spring, a lab, or a cloud, it's always H2O with the same elemental proportions. Ammonia, NH3, follows the same principle. If you decompose 17 grams of ammonia, you get 14 grams of nitrogen and 3 grams of hydrogen. That's a nitrogen to hydrogen mass ratio of about 4.67. Even though atoms combine in whole number ratios, their masses don't always work out to whole numbers. We use chemical formulas to represent compounds. These formulas show us what elements are present and how many atoms of each. For example, H2O tells us there are 2 hydrogen atoms and 1 oxygen atom. It's like the molecular blueprint for a substance. When writing chemical formulas, we don't usually show a subscript of 1. For example, in water, we write H2O, not H2O1. The 1 is omitted. It helps keep chemical formulas clean and easy to read. Here are a few common chemical formulas. NaCl is table salt with a 1:1 ratio of sodium and chlorine. CO2 is carbon dioxide, which has 1 carbon atom and 2 oxygen atoms. And C12H22O11, that's sucrose, or table sugar. These subscripts represent the fixed ratios of atoms that make each compound unique. Subscripts are sacred. Changing one gives you a different compound entirely. Take carbon monoxide, CO, it's toxic and deadly. Add 1 more oxygen and you get CO2, carbon dioxide, a gas we exhale and plants love. Always double-check your subscripts. When writing chemical formulas, we list the more metallic element first. So we say NaCl, not ClNa. For non-metal compounds, we go by position on the periodic table. Elements further to the left or lower down are listed first. So we say NO2 and SO2, not O2N or O2S. For non-metal-only compounds, chemists follow a general order when listing elements. It's based on their position in the periodic table. Further left and lower means they're more metal-like and get listed first. There are a few traditional exceptions like the hydroxide ion OH-. Some compounds contain groups of atoms that stick together and act as a unit. These are polyatomic ions. If you see parentheses in a chemical formula like in MgNO32, that means multiple identical groups are present. The subscript outside the parentheses tells you how many of that group you have. Break this formula down. 1 magnesium atom, Mg2+, 2 nitrogen atoms, 1 per NO3- times 2, 6 oxygen atoms, 3 per NO3- times 2, This kind of breakdown is important for understanding the atom count in a compound and how much of each element is present, vital for calculating dosage and reaction stoichiometry. There are three main types of chemical formulas. First, the empirical formula shows the simplest ratio of atoms. Second, the molecular formula gives the actual number of atoms in a molecule. Third, the structural formula shows how the atoms are connected. For example, hydrogen peroxide has the molecular formula H2O2 and the empirical formula HO. We use models to visualize molecules. The ball and stick model shows atoms as colored balls and bonds as sticks, emphasizing shape and angles. The space-filling model shows how atoms actually occupy space, giving a more realistic sense of a molecule's size and form. Let's look at methane. Its molecular formula, CH4, tells us it has 1 carbon and 4 hydrogen atoms. The structural formula shows that each hydrogen is bonded to the carbon. The 3D models help us understand the shape of the molecule, which is important for predicting how it behaves. Chemistry connects what we see with what we can't see. This image shows 3 levels: the macroscopic world, which we interact with every day, the atomic and molecular world, where the particles actually live, and the symbolic representations we use in chemistry, like formulas and models. Understanding chemistry means learning to translate between these levels. Substances can be elements or compounds. Elements can exist as individual atoms, like helium, or as molecules made of the same kind of atom, like O2 or N2. Compounds, on the other hand, contain 2 or more different atoms bonded together, and they can be either molecular or ionic. This slide organizes substances into categories. Are they elements or compounds? If they're elements, are they atomic or molecular? If they're compounds, are they molecular or ionic? This classification helps us predict properties, reactivity, and even biological effects. Atomic elements exist as single atoms, like helium or iron. Most elements fall into this category. Molecular elements exist as bonded pairs, like O2 or N2. You won't find single oxygen atoms floating around naturally. They pair up for stability. Here's a visual. Mercury is an atomic element made of individual atoms. Chlorine, however, is a molecular element. In nature, it comes as Cl2, pairs of chlorine atoms bonded together. These distinctions are important for understanding how elements behave in chemical reactions. Some elements are always found in nature as diatomic molecules, 2 atoms bonded together. These include hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. A handy memory trick: have no fear of ice-cold beer. Each first letter represents one of the diatomic elements. Molecular compounds form when 2 or more nonmetals bond by sharing electrons. Ionic compounds form when a metal and a nonmetal bond through electron transfer. This difference in bonding changes everything, from how the compound dissolves in water to how it interacts with the body. Dry ice is a molecular compound made of CO2 molecules. Each molecule is independent. Table salt, NaCl, is ionic. It's made of a repeating 3D grid of sodium and chloride ions. No individual NaCl molecules exist. It's one giant structure of alternating charges. When a metal gives up electrons and a nonmetal accepts them, you get an ionic bond. This forms cations and anion that arrange themselves in an alternating pattern. Unlike molecular compounds, ionic compounds don't form discrete molecules. They form crystals made of repeating units called formula units. To write an ionic compound's formula, you need to make sure the charges cancel out. Every formula must be electrically neutral. That means the total positive charge from the cations must equal the total negative charge from the anions. We'll look at how to do this step by step. Here's a simple 4-step guide to writing ionic formulas. First, write the symbols for the metal and nonmetal, along with their charges. Second, cross the magnitudes of the charges and use them as subscripts for the other ion. Third, reduce the subscripts to the lowest whole number ratio if possible. Last, double-check the total positive and negative charges must cancel out. Let's apply that rule. If aluminum forms a 3+ ion and oxygen forms a 2- ion, we cross the charges. The 3 becomes the subscript for oxygen and the 2 for aluminum. The resulting formula is Al2O3 With magnesium and oxygen, both ions have a 2 positive and 2 negative charge, so we only need one of each, MgO. Now things get a bit fancier. When working with polyatomic ions, groups of atoms that act like a single ion, you follow the same rule, but if you need more than one of the group, put it in parentheses. For example, if you need 2 nitrate ions to balance one magnesium ion, write it as MgNO3 Well, writing a formula is one thing. Naming it is another. Chemists follow systematic naming rules. Once you understand them, you can go both ways, from name to formula or formula to name. Many compounds also have common names like water instead of dihydrogen monoxide, but for science, we stick to the rules. When we name an ionic compound, first identify the compound as ionic. You'll know it's ionic if it starts with a metal and includes one or more nonmetals. That's your signal to use the naming rules for ionic compounds, not molecular ones. There are 2 main types of ionic compounds. Type 1 compounds have metals that form only one type of ion, like sodium or calcium. Type 2 compounds have metals that can form multiple ions, like iron, copper, or lead. This difference changes how we name them. In type 1 compounds, the metal has a fixed charge. Sodium is always Na+, calcium is always Ca2+. In type 2 compounds, the metal has variable charges. For example, iron can be Fe2+ or Fe3+. For these, we must indicate the charge using Roman numerals in the name. Here are some metals that always form the same ion no matter the compound. For example, zinc is always Zn2+, and silver is always Ag+. No need to specify the charge in their names. That's why we just say silver nitrate, not silver 1 nitrate. Some metals, like copper, lead, or iron, can form multiple ions. For instance, copper can be Cu+ or Cu2+. You must use Roman numerals to show which ion is present. So CuCl is copper 1 chloride and CuCl2 is copper 2 chloride. This distinction matters because the 2 compounds have different properties. Binary compounds contain only 2 different elements. For type 1 metals, the name is simple, just the name of the metal followed by the base name of the nonmetal with the ending ID. For example, NaCl is sodium chloride. That's it, no Roman numerals, no parentheses. Let's walk through an example, NaCl. Sodium is the metal and forms a consistent 1+ ion. Chlorine is the nonmetal, and we change its ending to IDE, giving us chloride. So the name of NaCl is sodium chloride. No Roman numerals are needed here because sodium's charge never changes. To name ionic compounds, you'll need to recognize the base names of common nonmetal anions. For example, F- becomes fluoride, O2- becomes oxide, and 3- becomes nitride. These roots are used consistently across compound names, so they're worth memorizing. When a metal can have more than one possible charge, like copper or iron, you must specify which one is present in the compound. For example, FeCl2 and FeCl3 are both iron and chlorine, but they're different compounds. Their names must reflect that difference. Here's a specific case. Cu+ is copper 1. Cu2+ is copper 2. The Roman numeral indicates the charge. So CuCl is copper 1 chloride and CuCl2 is copper 2 chloride. This small difference can dramatically change the compound's behavior and toxicity. The structure of the name is name of metal, followed by Roman numeral, in parentheses, followed by base name of nonmetal plus IDE. So FeCl3 is iron 3 chloride. The Roman numeral tells you the iron ion's charge is 3+, which is needed to balance 3 Cl- ions. Not sure what the charge on the metal is? Use the anions to figure it out. For example, in FeCl3, each chloride ion has a 1 negative charge. There are 3 of them, so the total negative charge is 3-. That means the iron must be 3+ to balance it, giving us iron 3. So putting that together, iron is the metal. It has 3 positive charges. Chloride is the anion. The full name is iron 3 chloride. Roman numerals make a big difference. They're like the zip code of a compound's identity. Polyatomic ions are groups of atoms that behave like one charged unit. When naming compounds that include them, we use the name of the polyatomic ion as is. For example, NaNO3 is sodium nitrate. You don't change the nitrate name. Let's look at a few examples. KNO3 is potassium nitrate. FeOH2 is iron 2 hydroxide. The Roman numeral tells us this iron ion is 2+. NH4NO3 has both polyatomic ions, ammonium and nitrate, so its name is ammonium nitrate. Just name each piece and you've got it. Some polyatomic ions contain oxygen. These are called oxyanions. Their names depend on how many oxygen atoms they have. More oxygen gets the suffix ATE like nitrate, NO3-. Fewer oxygen atoms use ITE like nitrite, NO2-. This naming pattern helps you understand chemical relationships between similar compounds. When we have more than 2 oxyanions in a series, we use prefixes too. Hypo means even fewer oxygen atoms than the ITE version. Per means more oxygen atoms than the ATE version. So for chlorine, we get ClO- is called hypochlorite. ClO2- is called chlorite. ClO3- is named chlorate. ClO4- is named perchlorate. These patterns are mirrored in other halogens like bromine and iodine. These ions aren't just lab jargon, they're all around us. Sodium hypochlorite is the active ingredient in bleach. Sodium bicarbonate or baking soda helps baked goods rise. Calcium carbonate is found in antacids like Tums. Sodium nitrite is used to preserve meats. Knowing their names helps connect your chemistry knowledge to real-world applications. Molecular compounds are made of 2 or more nonmetals. You'll often see these in biology and nursing chemistry. Their names use prefixes to indicate how many atoms of each element are present. These are not the same as ionic compounds, so the naming system is different. Here are the key prefixes to memorize. Mono means 1, di means 2, tri means 3, tetra means 4, penta is 5, hexa is 6, hepta equals to 7, octa means 8, nona is 9, and deca means 10. These go in front of each element to show how many atoms it has. A few naming quirks to watch out for. We usually drop the prefix mono on the first element. For example, CO is carbon monoxide, not monocarbon monoxide. When mono comes before a vowel, we often drop the O, so we say monoxide, not monooxide. This doesn't always apply to other prefixes like in triiodide, where we keep both vowels. Next up, acids. These are molecular compounds that produce H+ ions in water. Their formulas start with hydrogen, and we categorize them into 2 types. Binary acids, hydrogen with a single nonmetal. Oxyacids, hydrogen plus a polyatomic ion that contains oxygen. Each group has its own naming rules. This visual separates acids into binary and oxyacid types. Binary acids have only 2 elements, hydrogen and a nonmetal like HCl. Oxyacids contain hydrogen, a nonmetal, and oxygen, usually via a polyatomic ion like sulfate or nitrate. Recognizing the difference helps you apply the correct naming rules. Binary acids follow this formula. Hydro plus base name of nonmetal plus IC followed by acid. For example, HCl becomes hydrochloric acid. HBr becomes hydrobromic acid. When naming, make sure you're referring to the aqueous form. HClG is hydrogen chloride gas, but HClAq is hydrochloric acid. Let's name H2SAQ. The base name of sulfur is sulfur. Add the hydro prefix and IC acid suffix, hydrosulfuric acid. This naming pattern helps distinguish acids from other hydrogen-containing compounds. Oxyacids are named based on the oxyanion they contain. If the anion ends in ATE, the acid name ends in IC acid. If the anion ends in ITE, the acid name ends in OUS acid. Examples: HNO3 with nitrate becomes nitric acid. H2SO3 with sulfite becomes sulfurous acid. This is a key pattern to remember for acid nomenclature. This flowchart is your secret weapon for naming compounds. Start by identifying the type. Is it ionic or molecular? Does it contain a polyatomic ion or a variable charge metal? Is it an acid? Depending on the answers, the naming pattern changes. Use this chart like a GPS for chemical names. It'll guide you every time. Here's a cheat sheet of common oxyacids and their corresponding oxyanions. For instance, HNO3 is nitric acid from the nitrate ion, NO3-. H2SO4 is sulfuric acid from the sulfate ion SO42-. H2SO3 is sulfurous acid from sulfite SO32-. Knowing these pairs helps you go back and forth between names and formulas quickly. Again, this complete flowchart is your secret weapon for naming compounds. Start by identifying the type. Is it ionic or molecular? Does it contain a polyatomic ion or a variable charge metal? Is it an acid? Depending on the answers, the naming pattern changes. Let's practice naming with this list. CO equals sign carbon monoxide. CaF2 equals sign calcium. Let's practice naming with this list. CO is named carbon monoxide. CaF2 is named calcium fluoride. HFAQ is named hydrofluoric acid. FeNO33 is iron 3 nitrate. HClO4 is called perchloric acid. H2SO3 AQ is sulfurous acid. Keep these examples in mind. They illustrate all the major naming patterns we've covered. Chemistry is not just in the lab, it's in the clouds. Acid rain happens when air pollutants like nitrogen oxides, NO2, and sulfur dioxide, SO2, react with water in the atmosphere to form nitric acid, HNO3, and sulfuric acid, H2SO4. This lowers the pH of rainwater and damages ecosystems, buildings, and even human health. It's a real-world consequence of chemical reactions. Formula mass is the sum of the atomic masses of all atoms in a compound's formula. For example, to find the formula mass of NaCl, add the mass of one sodium atom and one chlorine atom. This concept is essential for converting between moles and grams, which is something you'll do a lot in healthcare chemistry. Let's summarize. Compounds have fixed compositions. Chemical formulas show which elements are present and how many atoms of each. Naming rules differ for ionic, molecular, and acid compounds. Formula mass is how we quantify the mass of compounds. These core ideas will show up again and again in your chemistry journey and in your future work as nurses. By the end of this chapter, you should be able to restate and apply the law of constant composition, write chemical formulas, count atoms in a chemical formula, classify elements as atomic or molecular, classify compounds as ionic or molecular, write formulas for ionic compounds, name binary ionic compounds with metals that form only one ion, name binary ionic compounds with metals that can form more than one ion, name compounds with polyatomic ions, name molecular compounds, name binary acids, name oxyacids with ATE ions, name oxyacids with ITE ions, calculate formula mass. Mastering these skills builds a solid foundation for the rest of the course and for interpreting the chemistry that matters in medicine.